My greetings to everybody. I hope everybody is well. So this is actually the last example on multiple reactors, and this would be the second part to this slide that I have prepared. So this will finish this particular problem. We already finished the entirety of the slide on multiple reactors. Now this is our third sample problem, and let me read the problem to you. So at present, the elementary liquid phase reaction A plus B, forming two moles of R and S, takes place in a PFR using equimolar quantities of A and B. Now, conversion is 96%, and initial concentration and A and B are equal at 1 mole per liter. If a backmix reactor 10 times as large as the plug flow reactor were hooked up in parallel with the existing unit, by what fraction could production be increased? Does the concentration level of the feed in this particular problem affect the answer in A, and in so, in what way? So there's a note here that conversion is to remain unchanged. So the question letter B has this continuation that even though we already hooked up a plug flow reactor or a backmix reactor 10 times the volume or size of the original plug flow reactor to it, will the concentration level of the feed to these two uh, parallel linked reactors affect the answer in A? But this one is to remain unchanged. So that is what is meant by letter B. So we will proceed with the solution of the problem. And let's go back to our board. So we will start with the given information. And this is number 3 already for this set of slide. So you are given a plug flow reactor and it has an original certain volumetric flow rate, let's say V1 entering it. Its volume, let's say we will represent as V sub P. And it's mentioned in the problem that there is a corresponding conversion of 96%. And we start with CaO and CbO being equal at 1 mole per liter. And there is this scenario, so I will make this one read that way. This will be the scenario that the problem is suggesting. So there will be a backmix reactor here that will be connected to the existing plug flow reactor. And of course, it will have its own volumetric flow rate. So they are parallel with the stream in here that is entering the plug flow reactor. And still we expect in this scenario that conversion is also still 96%. Okay, what else? So the reaction is given, and this is the stoichiometric equation or the chemical reaction. And okay, that's it. So conversion remains to be unchanged even though we already hooked up a backmix reactor to our existing plug flow reactor in parallel. The required information. So letter A is asking for by what fraction could production be increased? So what is the fractional increase in production? And letter B, if CAO or CBO is changed, will A, our answer in A, be affected? So if CAO or CBO is changed, will A be affected? And there's a corresponding or this is a succeeding question in what way. So I'll just write it here. If yes, in what way? So that's our problem, okay? But originally we only have this. Now we go to our next slide for the solution. So the first thing that we're going to do for this particular problem is, of course, write down the performance equation for each of our reactors. So in the original case, wherein we only have a plug flow reactor, so for our PFR, we know that the performance equation would be the volume of the PFR divided by its volumetric flow rate, which we labeled to be V1, should be equal to the integral of dCA over the rate. Okay. Now we can rewrite this expression since we know that let's us go back to the problem because we don't have specifically the rate law stipulated specifically in the problem. So we will read the problem again on what will be the corresponding expression for the rate law that we will write in here. So this is our problem. At present, the elementary liquid phase reaction. So this is elementary. So meaning whatever is the stoichiometric equation that would be our guide in writing the rate law. It's liquid phase. Then what do we learn about liquid phase? Automatically, the expansion factor, or that's the epsilon, will be equal to 0. So let's go back to our board. So we have this CAO to CA, we have DCA, and we have KCACB because it has to be elementary. And in our given, since we read in the problem that it's a liquid phase reaction, we will write here that epsilon A is equal to 0 because we have a liquid phase reaction. Okay, this is our expression now on the right side of our equation for specifically for the performance equation of the PFR. Now we need to change the expression for the rate law because our differential here is in terms of A. So there's a need for us to change CB as a function of A. So we write but CBO 1 minus XB is equal to CB. So if you'll have this expanded, that would be the left side, and this is equal to CB. Stoichiometrically, based on our chemical reaction, the amount reacting would be equal because the coefficients of A and B in our chemical reaction is just 1. So CaOXA is equal to CbOXB. And it was given also that CaO is equal to CbO. So the CbO I can change to CaO, and the CbOXB I can change to CaOXA, Cb. And what is this? This is actually your Ca. So your Cb is just equal to Ca. So therefore, this particular part in the rate law here can be rewritten as dCa over kCa squared. So this is now our right side of the performance equation for PFR. So let's have another sheet. So Vp over V sub 1 is equal to, so we can write this in terms of we can now evaluate rather the integral that we have here. We can write the k outside the integral symbol. So you have CaO to Ca dCa over Ca squared. If we will process the integration, this would yield 1 over k 1 over Ca minus 1 over CaO. Okay? Now, if we will substitute the available information that we have, so Vp over V1, both we do not know, is equal to 1 over K, which we also do not know. Now, your Ca is CaO 1 minus Xa. Your CaO is 1 mole, and your conversion is 96. So then this must be 0.04. So we can substitute the Ca value here, 1 over 0.04, and your CaO, which is 1 here. Okay. Now we have Vp over V sub 1 being equal to, so if you're going to process this side, this one, that would give you 24. So 24 over K. So this is our equation 1. So we're done with an expression for Vp, V1, and K, all of which are constants for the plug flow reactor. So now we can proceed with the MFR, which we will hook up in parallel with our PFR. So by the way, what we are processing here is the answer for letter A. So for the MFR, if you're going to write the performance equation for the MFR, that would be Vm over V2. And we have CaOXA over the rate. The problem, however, let me go back to the problem. The problem mentions that your backmix reactor is 10 times as large as the plug flow reactor. So we can have a relationship between the volumes of these two. Okay? Backmix is 10 times as large as the plug flow. So if you write it on our given information here, I think we have not written it. This the volume of this backmix reactor is 10 times that of the plug flow reactor. And we can go to our next sheet and have it written the same way. So I will write here 10 VP. I will have here V sub 2, and I'll have here CaOXA. I will have here K CaO squared 1 minus XA squared, because this one is KCa squared. So your Ca was already changed to CaO squared, quantity 1 minus XA squared. Okay, from this setup, we can cancel. We can cancel the CaO. We have one left here, and that's it. Okay, so we can have this expression 10 Vp over V sub 2 is equal to XA over K CaO 1 minus XA squared. Okay, so this is our performance equation for the MFR. And this is our equation 2. If you are a student, let's say I'll place myself in your shoes, and if I'm a student and I have already written the performance equation of these two, I may think, how may I be able to answer letter A, having these two performance equations? Because so far, if you're a student, you will simply think, I need to write down the expressions for the performance equations. And letter A requires you to determine the fractional increase in production. So if you go back to your expressions here for the performance equations of the two reactions, you have one here for plug flow, and you have another here for the MFR, or the back mix reactor. You have to think of which of the variables that remain, or which of the parameters that remain in our equation would aptly more or less give you an idea of how will production be increased. So you need to ask yourself, would that be the volume of the reactor? Now, you should never think of the volume of the reactor as a means of determining how will production be increased, because as per design, the volume is already fixed, just like it was stated already that the volume of the mixed flow reactor is 10 times of the plug flow. So there's nothing that you can do with it. So it's already fixed. In terms of conversion, it was already fixed. So conversion is fixed whether you only have one reactor, that is the plug flow, at 96%. And even if you were hooked up in parallel a mixed flow reactor to it, it would still be 96, because it was stated that conversion should be the same. CaO, there's nothing you can use with the CaO because it's an initial value and it's a constant. Same thing with the rate constant, because it's a very important characteristic of the rate law, which is dependent on empirical values derived. So that leaves you with the V2. So how will production be increased if you already have V2, another volume that is being added to the volume V1, which is simultaneously processed if the two reactors will simultaneously uh, process the feed, the same feed, and hooked up in parallel. So if you have only one reactor, then that would simply be V1. The volume that you will process would simply be, or the volumetric flow rate that you will process would simply be V1. But if you have already a second reactor, then you will have another volume that you will add with V1. So this will tell you how much would be the corresponding increase in production if you already have the presence of the MFR hooked up in parallel with the PFR. So that we can use these two equations and relate how will your total volumetric production be when you have already MFR hooked up in parallel with the PFR, we will divide equation 1 and 2. So it doesn't matter if it's 1 divided by 2 or 2 divided by 1, as long as you have a ratio of V1 and V2. So if you will divide, so divide 1 and 2, so you have Vp over V1 being equal to 24 over K. We will divide it by 10 Vp over V2 being equal to 600 over K. This 600 over K is the right side of the MFR, this one, if you substitute already the values. So you will have, wait lang. You can also have this CAOXA kept here. That way we will not have to worry about conversion, or you keep conversion there. So you will have here a 0.96 over a K times 1 times a 0.04 squared. That would give you 600 over K. So that's the 600 over K that we have in here. So after that, you can see that you can cancel this, and you will have a ratio of V1 to V2. So you have, so V2 over V1, this one goes up. This 10 I'd like to place here is equal to 10. By the way, you can also cancel the K's. So you will have 24 times 10, right? That will go there over 600. So your V2 is equal to 240 over 600 V1. This one transferred here. And V2 is equal to 0.4 V1. So now you will have a total volumetric flow rate of V1 plus V2. So your V1 is V1 and your V2 is 0.4 V1. So the total volume in the new scenario in which you have an MFR attached in parallel to your PFR would be 1.4 V1. The original, it's just V1. So how will you state the question of what's the fractional increase in production? Okay, that would be then this 0.4, because originally you only solely have V1. So therefore, production will increase by 40%. Okay, because of this part. Okay, that's for our letter A. Okay, so for letter B, it's actually the same scenario. You will simply have or you simply write up the performance equation for the two reactors, and then get the ratio of the two, because you are asked of the question. Let us go back. If CAO or CBO is changed, will A be affected? So will A be affected? So let's go back to our performance equations. If we will simplify our performance equation without having to substitute the values, let me have an expression. This one is already good because it's an expression. This one, for your plug flow, your expression would be 24 over K because we did substitute already the value. So I need to write here a more generic equation from here that will not have these values reflected. So I'll write here a different color. Okay. You have VP over V1 is equal to 1 over K. Then I will represent the CA in terms of CAO 1 minus XA. And I will have 1 over CAO here. Because I want to have a formula and check whether the formula will be dependent on initial concentration. The CAO and the CAO here can be written together with this with the K. And what I'll have here, if this is simplified, would be 1 minus quantity 1 minus XA over 1 minus XA. So this will cancel. And your formula, your general formula without values being substituted would be 1 over K CAO times the quantity XA over 1 minus XA equal to VP over V1 for your plug flow reactor. Okay? Now, for the mixed flow, I have it written here already without yet substituting the appropriate values. So what we'll do, we'll still divide these two equations. So you have need to divide 1 and 2 again. And if you divide 1 and 2, this will be your expressions to process. So you have VP over V1 equal to XA over K CAO 1 minus XA. Okay, that was our general formula for the performance equation of our PFR. And we have for the MFR 10 VP over V2 equal to XA over K CAO 1 minus XA squared. Okay, so we can now do cancellation. If we will cancel the common terms that appear here, so what will remain would be 1 over V1 is equal to 1, all over 10 over V2 is equal to 1 over 1 minus XA. I will transfer the V2 on top, so V2 over V1 is equal to, we can place the 10 there, 10 V2 goes up. Wait, class, so do you have here 10? Oh, you have 10 here. You can place the 10 here over 10 is equal to 1. So you have 1 minus XA. This one is like 1 is equal to V1, and this one is like actually this one goes up. So you have 10 here, and V2 goes there. V2 over 1 minus XA. So if you'll have V2, I'll place a box in here, huh? Because I'm simplifying our equation. So if it's V2 over V1, 1 minus XA goes there. So let me erase. So your 1 over XA goes up here with the V1, okay? And 1 over 10. So you'll have something like, I'll erase this one. From here, so this is the first thing that we did. 1 prime. Then this is our 1 double prime. Here, I'll place the XA on top, so you will have B1, 1 minus XA, is equal to 1, and you will have 10, sorry class, equal to B2. Okay, I place the 1 minus XA on top here. It goes with the V1. This it's equated to 1, and you have 10 here, and you will have V2. So you'll have V2 over V1 is equal to, okay, you will have 10 over, goes here, multiplication, good siya. So it's the same expression that we had a while ago. The ratio of V2 to V1 is 10 times 1 minus XA. And the thing is, class, if you could see here, our formula that will tell us of the increase in the production rate when we have already the backmix reactor connected in parallel with the plug flow reactor is, we have this expression on the right. And if you have to think of it, if you come to think of it, there's no concentration dependent expression on the right. You don't see a CaO here, and you don't see a CbO either, because we expressed everything in terms of A, the component A. So therefore, we can say that concentration will not affect A in any way, as long as we don't change the conversion. Concentration will not affect A as long as there's no change in the conversion. So that would be our answer for letter B. In the scenario that you have CaO or CbO changed. So even if we change the initial concentration of any of the species A and B, your answer in A will not be affected because your expression does not contain CaO or CbO on the right side. Okay? So this ends that topic on multiple reactors, the 3 examples with Sophie's. And you also have problems in Levin's field that you can practice solving. Okay? Let me go back to our slide. Our last part here in the slide is a group assignment. So one submission only for the group. I will also have it posted in Canvas that you will submit your submissions. You will have your submissions on the particular assignment requirement. So you have here the case wherein you have a back mix reactor followed by a plug flow reactor and another back mix reactor. You are required to determine the volume of each of the reactors. Now in here on the left side, you have the rate, the corresponding value of the rate given the conversion. So I think you fully already know how to process the essence or the importance of this pair of data. Why provide for the conversion and rate value for this particular reaction of butane, the isomerization of butane, which was carried adiabatically. So I will not tell you because I know you know, okay? That would be something that is just an application of what you've learned in determining the rate law from midterm. So this is how this is your only sole uh, graded requirement for as a group, graded group assignment for this topic on multiple reactors. Now I will, after this, I will record the set of slide for the recycle reactor, and that's it for chemical reaction engineering. Okay, thank you for listening, class. Bye for now.